a pleasure to introduce Vint Cerf. He is currently the Vice President and Chief Internet Evangelist at Google.
Is the mic not working? Just stick this in your left nostril.
No, you need to mute this.
Hey, here, let's do this.
Okay, there. Okay.
Is that good? Let's do a quick sound check.
Hello, can people people earlier in the world could hear us, so I'm assuming that they still can. Yep, okay, and that will go away in a moment. I've been lucky to know Vint ever since I took his networking seminar at Stanford well more than 50 years ago. And he was also very graciously was one of my thesis advisors. He has more honors. I could use half the talk talking about all his honors, including a Turing Award. But what he says is, if you want to know more, Google him. So, Vint, the floor is yours, and our ears we're waiting to hear what you have to say.
Uh-oh, you mean you actually expected me to say something useful? Okay, let me go. I thought I would just stand here and listen. Well, first of all, thank you for allowing me to consume some of your time today. I always look forward to these events because I have a chance to hear some questions, so I will try to leave time for questions. I can tell you that this has been a fabulous visit so far. I've had 2 or 3 meetings. Action items have come out of every single one of them, and I'm looking forward to coming back on the campus. This is a very stimulating place to be. It means a lot to me to be here for a special reason. My wife lost her hearing when she was 3 years old. And it's important that she was 3. She had spinal meningitis, but she'd already acquired language and sound. Her brain was adapted to sound. So she came to Johns Hopkins 50 years later after having spent 50 years lip reading only for communication, not sign language or anything else. And she got 2 cochlear implants here, one in 1996 and another one in 2006 to the other ear. So this place has a special meaning for us because she regained her hearing. And it was an interesting experience because when she came home after the first implant was done, she had to wait for a couple of weeks for everything to heal, and then she went back to be activated, which sounds vaguely religious, but what that means is they turned on the speech processor that maps the incoming frequencies to stimulus of a particular electrode. There were 16 electrodes embedded in her auditory nerve. So about 20 minutes after they turned this thing on, she picked up the phone and called me, and we had our first conversation on the phone after 30 years of marriage. It wasn't a deep conversation, but it was very emotional. Then I got home and I discovered I had a 53-year-old teenager at home. Couldn't get her off the phone, so if I called, the phone was busy. And then she decided that no decibel would go undetected. And so she started looking for additional devices. So a little microphone that plugged into the speech processor that she could clip to a lapel. So if she was walking down in a museum, the gallery docent could be talking and she would be hearing that with better clarity. The only technical thing she knows, and technical term she knows, is signal to noise ratio. And she knows the closer the microphone is to the mouth, the better the SNR. Then she decided that she would call the library and ask for recorded books for the blind because she wanted to hear words that she hadn't heard. So she calls them up. Remember, she's on the phone. And she says, can I sign up for recorded books for the blind? And they say, sure, no problem. You know, name, address, phone number. And then they say, now you're blind, aren't you? And she says, no, I'm deaf. And there's this long pause while they're trying to figure out how that's going to work. And she listened to some 500 recorded books over time. And now, of course, she detects accents and knows when people are mispronouncing things. She's got an FM transceiver, so if she were here, I'd be wearing a little FM transceiver around my neck, and she'd be getting the signal from 150 feet away. So she's very aggressive about getting good quality sound, and it's all thanks to the hearing center, listening center here at Johns Hopkins. But that wasn't the topic that I wanted to talk to you about today. This is about history and future of the internet. So first of all, it's important to know a little bit about how long ago a lot of this stuff evolved. So in 1961, Len Kleinrock was a student at MIT and got his PhD on using queuing theory to understand how message switching networks work. And message switching and packet switching are very similar, although that term didn't arrive until a bit later. Paul Barron was at Rand Corporation and was charged with figuring out how to build a communication system. In this case, it was digital voice, to design a command and control system that would survive a nuclear attack. And so his idea was that you would build a mesh of radio communication systems with, remember, this is 1962 when electronics were not quite what they are today. His idea was to put something, a little box of some sort on top of the telephone poles that would radiate in all directions, packetize the voice, and then transmit these message blocks. He didn't use the term packet. And he wrote an 11-volume series on this, only one of which was classified. But then he wasn't able to build the network because when he went to the Defense Communications Agency and described what this could do, they said it would never work, and the only way you should do voice is circuit switching. What's the matter with you? Don't you know we've been doing that since 1876? Get out of here. So he never got to build it. But a guy named Donald Davies at the National Physical Laboratory in England also cottoned on to this idea of packetization and built a one-node network. And he couldn't build more than one because they didn't give him enough money. So he built what I would call the first local area network, running at 1.5 megabits a second. And he coined the term packet. He consulted with I guess a linguist to see what the right descriptive term should be. So he invents the term packet. And then in 1969, in 1968, DARPA asked the Defense Advanced Research Projects Agency wanted to build a packet switch network. And the reason they wanted to do that is that it was already funding a dozen or so universities to do artificial intelligence research way back in the 1960s. And some of you will remember that the term artificial intelligence hits in 1956 when John McCarthy was at a conference at Dartmouth, and they speculate about this. So ARPA's funding research on artificial intelligence in the 1960s. Everybody keeps asking for a new computer every year, and DARPA can't afford to build or buy a dozen different supercomputers every year. As they said, we're going to build a network and we're going to connect everything together and you can share your resources. And oh, by the way, we're funding everybody. So don't hide your work, share your work, let everybody get access to the software and the hardware to accelerate the pace of AI. Now, of course, it didn't accelerate all that fast, did it? Because it's taken 60 years or so to get to where we are today. But the ARPANET was designed for purposes of resource sharing, not for purposes of surviving a nuclear attack. And a lot of people misunderstand that the ARPANET and the internet were intended to survive nuclear attacks. I guarantee you it's unlikely that even today's internet would survive a nuclear attack. But a lot of pieces of it would probably survive because we lose pieces of it every day because of cable cuts and other things, and it still works. But it was not intended to survive a nuclear attack. So when you read that, you should discount it as a mistake. The first public demonstration of the ARPANET was in 1972 in Washington, D.C. And I participated in all of this stuff because my undergraduate work at Stanford started in 1961. And that's when John McCarthy had gone there. So I've been exposed to the whole sequence of AI, which is not going to be my topic for today. So this is what the original ARPANET looked like. It was just a 4-node system. I was a graduate student at UCLA, and my job was to write the software for the Sigma 7 machine, which is in a museum now. And some people think I should be there too, but here I am, still chugging along. The imps were refrigerator-sized machines. This is what you stick in your pocket today, but This thing was delivered to UCLA in September of 1969 in a very, very heavy metal container. BB&N, Bolt, Beranek, and Newman, which built this thing, this is a Honeywell DDP 516 or 416, maybe 316, probably a 516. And they knew it was going into a very hostile environment, namely a collection of graduate students. So they put it in this heavy metal container to protect it. And that's it's still at UCLA on display in room 3420, which is where Kleinrock has maintained a little museum of the ARPANET. So the internet problem arrives, at least in my lap, when I'm at Stanford. I went there from UCLA in late 72, and in early 73, Bob Kahn shows up. He's gone from Bolt, Beranek, and Newman, where he was very much involved in the ARPANET design, to ARPA, and the project that he was going to work on got canceled, and so he had to come up with something else. And so he shows up in my office and he says, you know, we've got this network, this ARPANET thing, and it connects computers together. Some people think that maybe computers could have a role in command and control. But the implication of that is, first, that it has to carry voice, video, and data. And the second implication is it's going to have to be in ships at sea, airplanes, and mobile vehicles. Well, we built the ARPANET out of dedicated telephone circuits, and it doesn't help to connect the ships with wires because they get all tangled up. Planes never make it off the tarmac, and the tanks run over the wires and they break. So he had already started working on mobile radio communication, digital packetized radio communication, and packet satellite communication, using Eutelsat 4A over the Atlantic to connect the western part of Europe to the eastern part of the US. So he shows up with these three different packet switch networks, and they're all different addressing structures, different routing strategies, different speeds, different latencies, different packet formats. And the rule was, he said, well, how do we connect them all together so they look the same? And he said, by the way, you're not allowed to change any of them. I said, oh, okay. So, you know, when you have constraints like this, it's easy, right? You know, so I would draw these little cloud-like things to represent a network, which, by the way, is where the term cloud computing actually comes from. We used to draw little clouds because we didn't care what was going on inside. We only cared it was a network, and anything that connected to it could talk to anything else that was connected to it. So we said, okay, we got these little cloud networks, and then we had to interconnect them with something. And they don't know how to talk to each other, so we better stick a box in between. And then we said, well, should we try to translate, you know, one network format to another? And that's an n squared problem. We thought it was a bad idea. Why don't we do something uniform? So we invent the notion of internet addresses. So we could say, a host on one machine could say, send this to that computer on that other network. And of course, the network it's attached to doesn't know that there's another network. But the box in between, we call them gateways. We didn't know they were supposed to be called routers. We call them gateways, and they figured out how to route the packet to through the next network, and hop by hop get to the final destination. So it takes us about 6 months to figure all this out, from the spring to the fall. We write a paper, which we present a summary of at the University of Sussex, and then we publish a paper in May of 1974 in IEEE Transactions on Communications. Now, interestingly enough, just down the street from my office at Stanford is Xerox PARC. And just as Bob and I are starting to work on the internet design, Bob Metcalfe and David Boggs are figuring out how to do Ethernet as a consequence of Bob Metcalfe's visit with Steve Crocker when Steve was working for ARPA, seeing an article about the AlohaNet in Hawaii, and he goes out to visit the guys there and says, you know, that's a really clever idea. I can do it about 30,000 times faster on a coaxial cable. So he and Boggs figure out how to do Ethernet at what was 3 megabits a second at the time. So there are 4 packet switch technologies now that Bob and I are wrestling with, trying to figure out how do we make it all look uniform. And so that's how the basic that's how the basic internet problem was posed to me by Bob. And I want to make sure you all appreciate Bob is the one that came up with this idea. And then he asked me if I could help him. And I think there's a life lesson hiding in there for you. If you want to do something big, go get help, especially from people who might even be smarter than you are, although I am not smarter than Bob Kahn, I guarantee you that. So when the packet radio idea got started, Bob had commissioned Collins Radio in Texas to go build packet radios. And then he commissioned Stanford Research Institute, now SRI International, to go and actually implement the system by populating the Bay Area with packet radios, some up on the mountains and some in mobile vehicles like the packet radio van. There are many stories about this van because it's not marked in any way. And they used to drive up and down the Bayshore Freeway, and it would pull off to the side of the road in order to measure shot noise and how much interference were you getting from the generators in the cars that were going by. And there's a story that, of course, it was engineers who were doing this. So one day they pull off to the side of 101, and the engineer who was driving goes into the back with the rest of the guys. And so a cop goes by and he sees this nondescript thing with a stacked dipole array antenna coming up the top. And there's nobody in the cab. So he goes around, he knocks on the back door. The door opens up, and all these geeky looking guys with beards and displays and radios. And the guy looks at him and says, "Who do you work for?" And he says, "Oh, we work for the government." and the policeman says, "Which government?" "But officer, we're only going 50 kilobits a second." So the packet radio van is now at the Computer History Museum, and it's a wonderful exhibit. Just to show you what packet switching was like. Now, remember I showed you the EMP that was a refrigerator size. The packet radios shrank down to a cubic foot. They weighed about 35 pounds and cost $50,000 each. We had 4 of them in the van, which supplied not only mobility, but also power. And just to show you how advanced we were working on, during that time period, packet speech, packet video, tracking data, and text messaging, and things like that. That was all motivated by the command and control requirement. And as you can see here, we used very advanced telephone technology here, the Mickey Mouse phone. This was really very important, though, because voice communication is a critical part of command and control. Now, those of you who know a little bit about packetizing and digitizing speech will know that the normal thing to do is to sample the voice at 8,000 times a second and get 8 bits per sample. So that gives you 64 kilobits a second. If you differentially encode it, it's 32 kilobits. And the backbone data rates we had in packet radio were up to 100 kilobits a second, in some cases, maybe even 400. And then on the ARPANET, the backbone speed was 50 kilobits a second. You can't put a lot of 64 kilobit speech in a 50 kilobit channel. So DARPA, the Information Processing Techniques Office, was investing in a variety of different encoding schemes to reduce the bandwidth required to carry digitized voice. One of them was called linear predictive code with 10 parameters, which models the voice tract as if it's a stack of 9 cylinders whose diameter is changing as you speak, and it's activated by a formant frequency, which you can think of as pitch. You send those 10 parameters to the other side, and then inverts the calculation and produces sound. Now, we were shrinking this down from essentially 64 kilobits to 1,800 bits a second. And when you do that, you lose a certain amount of quality. So anybody that talked through the system sounded like a drunken Norwegian. And so I'm at ARPA and in the mid-70s, and I got to demonstrate this to a bunch of generals, and I'm trying to figure out, okay, so how am I going to do this? And then I remembered that Ingvar Lund at the Norwegian Defense Research Establishment was part of the packet speech experiment. And so I got him to talk first through the Autovan system, which is the ordinary switch voice system, and then through the packet radio, packet speech system, and it sounded exactly the same. And I never told the generals that everybody would sound that way. I don't have a demo for you here, but we were also working on packetized video at very low data rates, small numbers of frames a second. Of course, you can see where we are today, that literally right this moment, we're using a considerable amount of bandwidth to move video and audio back and forth on a distributed network, which spans the globe. Fast forward a little bit to 1977. I'm running this program, the internet program at ARPA, and I really want to demonstrate that this stuff works, and I want to do it in a way that I can show my superiors that it's not crazy to imagine an arbitrarily large number of networks all being interconnected and interworking. So we do this 3-network demo. I'm in Washington at the time. We have the packet radio van driving up and down the Bayshore Freeway, radiating packets that are going to a gateway linking into the ARPANET. Now, the ARPANET, in the meantime, has been expanded with an internal geosynchronous satellite hop all the way to Europe, to Sweden, and then Norway, and then down to the University College London on a landline. So the packet goes into the ARPANET, goes all the way to London, and hops out of London and goes into a packet radio gate or packet satellite gateway, which then goes back through another synchronous hop through Intelsat 4A, and then lands at another gateway in Etam, West Virginia, and then goes back into the ARPANET and all the way across the country to USC Information Sciences Institute in Los Angeles. Well, San Francisco and LA are about 400 miles apart, but the packets have gone at least 88,000 miles because they've gone through 2 synchronous satellite hops back and forth, plus across the US. And it works. And I'm leaping around in my office screaming, it works, as if it couldn't possibly work, right? And this is software. It's a miracle when software works. You should all appreciate that. So this was a very important milestone, in my view, of the internet, because we demonstrated 3 very different networks and eventually more, like the Ethernets and everything else. So that was a big, important day. So at that point, I said, okay, well, we're now going to go for gold, and we're going to implement this on every operating system we can get our hands on. Now, you have to keep in mind that in the mid to late 70s, there were actually a lot of operating systems. It wasn't all Unix, et cetera, so, or iOS and so on. So I started working on getting companies that had operating systems to go implement TCP/IP. And in particular, I went to IBM and Digital Equipment Corporation and Hewlett-Packard. But I went to the research labs because they all had research labs at the time. And so I didn't go to the commercial side. I went to the research side, and I said, would you guys like to participate in this thing? And would you like to be part of that? And of course, the engineers are saying, yeah, this is really cool. So they all implemented TCP/IP in their operating systems. Later on, of course, the commercial guys didn't want to have anything to do with this. Digital was going down the OSI path with DECnet, 4, DECnet 5 was going to be OSI. IBM had SNA, and they didn't want anything to do with it. Ellen Hancock didn't want to have anything to do with this TCP/IP stuff. An example of what would happen as the internet became more visible is that the commercial sales guys would bring an engineer along with them to a customer in order to answer any technical questions the customer would have. And so occasionally, as the internet becomes more visible, a customer would say, yeah, I know about SNA, but what about this internet thing? I can use other companies' computers to interconnect to yours. And of course, sales guys said, why would you ever want anybody else's computer but ours? I said, well, there are mergers and there are other things. And then the engineer would say, oh, we have that operating in the lab. So eventually, these companies who had their own networking capability had to give up and adopt and implement the internet protocols. So it comes January of 1982. And John Postel, who was the RFC editor and the Internet Assigned Numbers Authority allocating IP addresses and domain names, and I decide that we're going to announce on January 1982 that on January 1, 1983, everyone on the ARPANET and any of the other networks that DARPA supported had to be running TCP/IP or you're off the net. And so I announced that as the program manager. And we get some grumbling, but I've got a guy named Dan Lynch at ISI tracking who's implemented TCP/IP. Now, you have to know there are only 400 computers on the network at the time, as opposed to 400 million or something. So I'm tracking this, and around summer or so, the additions flatten out. So I thought, oh, okay, well, some of it's summertime, but, this is not okay. So I called the Defense Communications Agency, which was responsible for running the ARPANET at the time, and I said, shut off the capability to carry anything except TCP/IP for one day, just 24 hours. And, they salute and they do that. The phone goes off the hook, what's the matter with you, you idiot? I can't do my email, blah, blah. I said, I just want you to know I can do that. And the curve starts going up again. Then around October, it flattened out again, and I called DCA and said, shut it off for 2 days. And of course, the phone rings. We managed to get almost everybody up running on TCP/IP by January 1, 1983, except for a couple of stragglers, and we gave them a couple of extra months to get on. So Flag Day, you couldn't do a Flag Day again. I mean, we could only get away with that for a couple of reasons. One of them is if you're not running, you're off the net, and I won't fund you anymore. That was a very powerful argument. So it's good to be on the correct side of the checkbook. And I'm sure, Greg, you can appreciate that specifically. So the mid-1980s come along. Our internet is running as of January 1, 1983. The Department of Energy and NASA and the National Science Foundation decide there's good reason to adopt the use of internet technology so that they can connect their laboratories together or connect universities to supercomputers that are being funded by NSF and the Department of Energy. So the four networks, ESNet and NASA Science Internet and the NSF Net, join ARPANET as part of the backbones of the internet during that period of time. But it's important to appreciate that only people with government research support had access to the internet at the time. The Defense Department and these others, but not the general public and not the private sector. So around 1988, I remember going into an exhibit called Interop, which was started by Dan Lynch in 1986. By 1988, 50,000 people showed up at the Moscone Center to see what this internet thing was about. They were seeing products like Cisco systems and other local area networks from 3Com and so on. And they were seeing software, they were seeing things interacting across an Ethernet, big yellow cable, coaxial cable. So 50,000 people show up, which is kind of astonishing. And I went walking in with Eric Benamou, who was the then CEO of 3Com. And I turned to Eric and I said, Eric, we're looking at a Cisco, 3-story high Cisco display. And I turned to Eric and he said, how much do these things cost? And he said, about $250,000. That was a lot of money in 1988. So I'm standing there with my jaw on the floor thinking, my God, somebody thinks they're going to make money out of the internet. And then I got to thinking, how are we going to get the private sector and the general public onto this system? Because it wasn't permitted. There was an appropriate use policy that said no commercial traffic will flow on the government backbones. So I'm trying to figure out how to break that rule. And I had done some other work in an earlier period for a company called MCI. We built a commercial email service called MCI Mail. So I proposed to the Federal Networking Council that I should try an experiment to connect the commercial MCI mail system to the internet to see if we can make them work. Well, since I'd worked on both of them, I knew how to do that. So it wasn't really an experiment, it was just engineering, but I didn't tell them that. So they said, okay, you can do that. And I thought, wow, that's cool. So by summer of '89, we're demonstrating this flow of email across the internet from the MCI mail system. And then all the other commercial email guys, Telenet and TimeNet and all the others, see that and they say, well, wait a minute, we don't want those MCI guys to have this special privilege. We want to get connected. And the Federal Networking Council said, okay. And the result was that they all got connected to the internet. Then they discovered that their little fiefdoms were suddenly penetratable, porous, because everybody on their network could talk to everybody on the other networks going through the internet because they're all using the same protocols. So that kind of shocked everybody for a bit. But the result was that in 1989, late 1989, 3 commercial services got started in the United States offering TCP/IP service to the general public and the private sector. UUNet was the first of them. It was started in Virginia Rick Adams was the CEO. It started as a nonprofit company in 1987. It became an internet service company a couple of years later. And then in 1997, I think I have this right, they are acquired, yes, they're acquired by a company called WorldCom. Actually, they were acquired by Metropolitan Fiber Systems for $2 billion. And then on the same day, Metropolitan Fiber Systems was acquired by WorldCom for $14 billion. So Rick Adams sold all of his shares and retired as a billionaire. And then PSINet got started out of New York, but it was headquartered in Virginia. And then there was General Atomics out in California that started something that they called SURFnet. And they had a whole, ad campaign surfing the internet and all that. And then they discovered, after they gotten all this worked out, that there already was somebody called SurfNet in the Netherlands. It was a nonprofit that connected universities together in that country. So they had to change their name. And somebody said, well, why don't we change our name to the California Educational Research Foundation Network, SurfNet. And then somebody else says, maybe we should call Vin. So they called me up and they said, is it okay if we call our network SurfNet? My first reaction was, if they screw it up, am I going to be embarrassed? And I thought, well, wait a minute. People name their kids after other people. And if the kids don't turn out right, they don't blame the people they name them after. And I said, sure, go ahead. So in July of '89, I flew out to San Diego, and Susan Estrada, who was the director of SurfNet at the time, and I took a bottle of glitter and we smashed it over a Cisco router and we launched SurfNet. So that's the beginning of the commercial activity. And this is just a representation of the kinds of large-scale networking that National Science Foundation, DOE, and NASA were doing during that mid to late 1980s period. It was very, very important that that this was a demonstration that the basic idea of multiple networks being interconnected was feasible. And of course, the data rates were going up dramatically during that period. When the 1990s come along, especially late 1991, Tim Berners-Lee announces the World Wide Web. And to be honest with you, not too many people noticed that. If you remember, or maybe some of you weren't even around then, but if you read, his original design was text-based. So it wasn't imagery. You could display images, but it was a text-based system. The guys at the National Center for Supercomputer Applications, Mark Andreessen and Eric Bina, in 1993, thought it would be interesting to have a graphical user interface. So they developed something called Mosaic. And that was a dramatic change because the internet suddenly looked like a magazine with formatted imagery and text, and eventually, of course, streaming audio and video. And the founder of Silicon Graphics saw this and said, this is a BFD, this is a big deal. And he brings Eric and Mark Andreessen to the West Coast to start Netscape Communications in 1994. And just as a side note, ironically, in '94, I returned to MCI after having spent 8 years with Bob Kahn and his company, CNRI. And they said, can you put us in the internet business? And I said, yeah, I could do that. So in '94, I go out to Netscape Communications and buy $7 million worth of licenses so I can use their technology to build a shopping mall. Now, ironically, I'm doing this shopping mall thing for MCI. Guess who else is doing a shopping mall? Jeff Bezos has started Amazon. He did better than I did. And I freely admit that. But the point is that the next year, in 1995, Netscape Communications went public. This, after only a year of existence, was very unusual. The stock goes through the roof. The dot boom is on. Silicon Valley investment companies are throwing money at anything that looks like it might have something to do with the internet. So we have this dot boom period that goes on for about 5 years, and then around April or May or so of 2000, everything goes kaput because a whole lot of those startups had CEOs that didn't know the difference between capital and revenue. Capital is finite, revenue is what keeps the company going. You don't got any revenue and you run out of capital, you're dead. So the landscape is littered with a lot of dead startups. But some of them survived. Amazon didn't do too bad. Google got started in 1998. They didn't do too badly either. So that boom period was important for a couple of reasons. One of them is companies got started, some surviving well. And then there was this rapid proliferation of web pages, so much so that you couldn't find anything. And so there were a variety of attempts to help find things on the web. Alta Vista, some of you may remember or have read about. Yahoo was next, the whole company got started. Google came along, Microsoft does, Bing later on. So search engines come along and make the internet accessible through the World Wide Web and the indexing that's been going on. Of course, that's been an important story for the last 20, almost 30 years now. So I'm cheating a little. This says Internet Now, but this picture was actually generated in 1999. But that's from the the BGP routing tables. But it lets me point out something. The colors represent different networks. There are tens of thousands of networks in the internet, maybe even more if you consider your home network to be one of them. And the reason this is so interesting is that everybody who's running a network gets to choose the hardware they want. They get to choose the software they want. They choose the business model they want. They choose who to connect to based on whatever terms and conditions they can arrange. And the whole thing still works. And the reason it works is they're all using the same protocols. And also there is one organization. This is not centralized. The system is not centralized. It's very distributed. But there is one organization that tries to keep order in the IP address assignment and the domain name system, so uniqueness is maintained. So the Internet Corporation for Assigned Names and Numbers, ICANN, is responsible for allocating IP address space on a unique basis and domain names similarly. And of course, there's a whole structure associated with that, regional internet registries and the like. So this whole thing hangs together because of a collaborative and cooperative choice among all these various parties. Of course, in the 2000s, and this is getting into territory that many of you have experienced and grown up with, the iPhone shows up, and that is transformative because suddenly you can get to the internet when you're in mobile operation. So this is packet radio all over again in your pocket or your purse. Now, interestingly enough, mobile telephony actually has its origins way back in 1973. It turns out that Marty Cooper is working on the design of a mobile telephone system in the same year that Bob and I are starting to work on the internet, and Metcalf is starting to work on the Ethernet. I did not know anything about Marty's work until 1983, the year that we launched the internet, because that's his first demonstration of mobile telephony is 1983. So a guy named Danny Cohen invited me to lunch early in 1983. He said he had something to show me. And I said, what is it? And he said, well, come to lunch and I'll show you. So I came to lunch and he's got this thing sitting on the table. And I said, what's that? And he said, it's a phone. He said, well, it's about this tall. It's got a whip antenna. And I said, what is it? And he said, it's a telephone. And I said, where are the wires? And he says, there aren't any. He said, well, how does it work? So we were chatting for a while and he says, you know, I don't know the answer to that. Why don't you call the guy that invented it? So I take this brick, his 2.5 pound brick, and I call Marty Cooper and introduce myself. And I said, Marty, how long does the battery last? And he says, 20 minutes, but you can't hold it up longer than that anyway. It weighs too much. So Marty has become a dear friend. He's 95 years old, going strong. It's just amazing. So this is a huge transformation, is the iPhone. And then, of course, social media come along, and that's had transformative and not necessarily always good side effects. And so many of us are very conscious of the fact that some of the harmful activity on the internet is a consequence of people abusing the technology. It's like an amplifier, and it can amplify bad stuff as well as good stuff. And that's a struggle. That's a policy issue, and it's also a technical and policy challenge, a legislative challenge. Then come AI transformers. And there's this long 60-year history, which I won't try to repeat, which leads us to that point in the mid-10s, and now, of course, massive generative AI systems. So I'm not going to spend time on AI for a couple of reasons. One of them is I'm running out of time. But I just want to remind everybody that it's been a long history, over 60 years to get to where we are right now. And there's still a lot of work to be done in spite of the fact that the systems have become incredibly useful, even though they do have hallucination problems and a few other things that are non-trivial to deal with. But I'm not going to spend time on this slide just because I want to get to some other stuff, which is another topic that got started in 1998. So this is expanding the solar system, expanding the internet to run across the solar system. So some of you may recall that in 1976, Viking 1 and Viking 2 landed on Mars, and this was a major accomplishment. It really, think about it, 1976 is 50 years ago. Then for 20 years, nothing works. You know, we miss the planet, burns up in the atmosphere, hits the ground. But in 97, the Sojourner, the little robot, in the Pathfinder mission lands successfully on Mars and sends signals back. I get so excited after 20 years of nothing. I fly out to the Jet Propulsion Lab to go talk to the team that's doing communications for that Sojourner. And within a few minutes, we're completing each other's sentences. And then we're asking ourselves, what should we be doing in 1998 that we're going to need 25 years from now? And we decide we should design and build a solar system-wide internet to support manned and robotic space exploration. So we start work on that. Now, there are some problems associated with communications in deep space. One of them, of course, is just getting the hell off the planet because of all the debris that's out there. But there are natural disruptions, you know, solar flares and things like that. There's radiation out there that can affect the electronics of things you do. And then there is the problem of distance. You know, space is big, and there's this thing called the speed of light. And then there's disruption that takes place as well. You know, the planets are rotating, and we don't know how to stop that. So if you're talking to something on the surface and the planet rotates, you have to wait till it comes back around. Same problem with the satellites. So we start out in 98 thinking, well, you know, why don't we use TCP IP for this? Works okay on Earth, it ought to work on Mars. And it probably will. And then we start doing the math. Well, let's see. The closest we are to Mars is 35 million miles. Do the math. It takes about 3.5 minutes for a radio signal to go from Earth to Mars and another 3.5 to come back. When we're farthest apart in our orbits, it's 20 minutes one way, 40 minutes round trip. Flow control doesn't work really well for that, because basically TCP flow control says, I can't take any more. And the other guy is supposed to stop. And if it's a half a second before he hears it, it's not too bad. What if it's 20 minutes? He's pumping data at you for 20 minutes and you don't know what to do with it. So that didn't work very well. And then there's the planet rotating problem. So we have a variably delayed and disrupted environment. We needed a whole new suite of protocols. We call them the bundle protocol because bundle sounds sort of like packet. But it does a few things that the internet doesn't do, one of which is to store information in the network. So the routers effectively become storage devices. So let's say, for example, in the case of internet, if you get to a router and the router says, I have no route to get to the destination, it throws it away on the assumption that you can retransmit from the source. But imagine you're trying to go from Earth to Jupiter and you got to the Mars relay. Now, you had to work pretty hard to get to the Mars relay in the first place. So now what are you going to do? Throw the data away because you can't see Jupiter yet? Well, that's dumb. So we said, okay, we'll store the data in the network. And when that link becomes available, we will transmit the data. The IETF has just finished doing a working group on time-varying relay or time-varying routing as one investigation of that kind of network environment. So we've developed, we being the Jet Propulsion Lab team, the NASA team, the European Space Agency, the CARI, and JAXA have all been working together to finalize the design and specification of the bundle protocol suite, which is an implementation of delayed and disruption tolerant networking. So it's all been standardized both by the IETF and the Consultative Committee on Space Data Systems. When Spirit and Opportunity landed in 2004, they were going to transmit data directly from the surface of Mars to what's called the Deep Space Net. Those are 3 70-meter dishes in Goldstone, California, Madrid, Spain, and Canberra, Australia. So that was the plan, direct from Mars to Earth to the Deep Space Net. And they fire up the radios and they start to overheat. And, you know, the engineers say, oh, okay, we're just, oh, by the way, they're only getting 28 kilobits a second. And so the scientists are already a little grumpy about that. Now we tell them we have to back off on the duty cycle to keep from damaging either the equipment or the sensors or the radios. Now they're really grumpy. But one of the guys at JPL says, well, you know, there's an X-band radio on the rovers. Yeah. He says, well, you remember we sent the orbiters a couple of years ago to map the surface of the planet to figure out where the rovers are supposed to go. Well, they have an X-band radio and they still work and they have memory and computing and so on. So we said, we got some prototype software. Would you like to try that? And they said, yes. So we uploaded our prototype bundle protocol software to the rovers and to the orbiters. And for the last 20 plus years, all the data coming back from Mars has been stored and forward through the orbiters back to Earth, to the Deep Space Network. Oh, by the way, because the orbiters are not very far away from the surface, we could transmit at 128 kilobits a second. And because the orbiters are outside of the thin atmosphere and have bigger solar panels, they can transmit at 128 kilobits to the Deep Space Net. So they get 4 times the data back than they were originally going to get because we're doing store and forward. So even a small little network like this has real benefit. So we're at the point now where all of the rovers that have been sent since Spirit and Opportunity have used this prototype system to deliver data back. There is a special interest group, which you can go to. It's ipnsig.org, that is also actively involved in testing and deploying terrestrial deployment of the bundle protocol suite. All 4 of the major space agencies, NASA, ESA, JAXA, and CARI, are engaged in participating in implementation and testing. There's multiple implementations of the bundle protocol suite on different operating systems. And we are preparing to support the Artemis return to the moon mission and the Gateway mission as well, assuming that they go forward. So if you're interested in learning more about what's happening, ipnsig.org is a good place to go to just see what's happening so far. We're anticipating that there will be a lot more activity on the moon, as you all know, from Artemis and the Moonlight mission out of ESA. There is an attempt to make sure everything is interoperable by adopting and using the bundle protocol suite. By the 2030s, we will see many, many more of these systems in operation. We're confident of that. But there are some really interesting problems that are coming. And for some of you who are interested in this, I hope you'll start working on them. We're commercializing space, as you know, and there are a number of commercial companies like Intuitive Machines and Illyria and Relativity Space and others. The commercialization of space has a lot of implications that and ramifications that are not yet fully understood or worked out. There's an outer space treaty from 1967 that says nobody's allowed to own any property off the planet. So you can't claim property on the moon. Well, what happens if you land on the moon and you want to build a mine because NASA said they'll buy your output from the mine? So you're the CEO of the company. Your first question is, can I own the property? And the answer is no. He said, well, can I register it somehow? And the answer is, I don't know. Where would you register property on the moon or on an asteroid on Mars? And nobody has a good answer to that right now. Well, what happens if somebody interferes with my operation? Well, I don't know. Do you call the Space Force? We don't have good answers to the implications of commercialization of space. And there are going to be all kinds of things that are certainly on the moon. There will be rovers, there will be habitats, there will be laboratories, all kinds of other things that companies are going to make and that the spacefaring nations are going to purchase. And something very important has happened consequence of SpaceX and Blue Origin as well. And that's that countries that didn't have a space program can have one now because they have the ability to get to space at a reasonable cost. Before the reuse of the first stage, it was really expensive. It's still not cheap, but it is less expensive to get into space than it ever was before. I used to work on the F-1 engines of the Apollo program way back in the early 1960s. I was at Rocketdyne doing software to evaluate the tests of the F-1 engine. This is a 1.5 million pound thrust engine. There were 5 of them on the Saturn V rocket, 7.5 million pounds of thrust. And we had no intent to reuse the first stage at all. So all I needed to do was to assure that it would not fall apart until after it ran out of fuel, after which we didn't care. Now, of course, Musk and others have decided reusing the first stage makes a lot of sense instead of flying from New York to Los Angeles in a 747 and throwing the 747 away, which is a great analogy. So we are anticipating a very, very active and vibrant commercialization of space. So there are all these questions you can see at the bottom of the slide. What do we do about, what does sovereignty mean? And, there aren't any countries off the planet. So what does it mean to exercise sovereignty? And what if you encounter space junk? I mean, do we have rules for salvage? What about agreements on emergency aid? I mean, if you look at the rules for operating on the open seas, there are a variety of conventions that we've adopted for dealing with salvage and rescue and all that. We don't have those codified at this point. And as much as we might not like it very much, space is already militarized. We have a space force. Well, we have concerns about what other countries are capable of doing to our satellites, for example, and probably vice versa. What about contamination of a site? What about heritage sites? What about the sites where we landed on the moon in 1969? We'd like to preserve those, I would think. So what rules should there be? We don't have answers to a lot of these questions, and we need them not 30 years from now, not 10 years from now, because we're going to have these problems in 2026 or 27 or 28. So there is a report describing a lot of these issues and some of the thoughts that you might find interesting, and you'll get it at the IPN-SIG site. And that's all I have for this morning, and we have a little bit of time for Q&A. So thank you very much for the time. Yeah, that was bad. I forgot that we are online. I don't know whether did I come back? Oh, I'm still sharing screen, right? So I have to fix that. Hold on. It's not sharing. Oh, because I shut it off. So I need to rejoin.
No, you're on.
Am I still on? Oh, okay. Oh, but I see what's wrong. I need to go.
This is on.
Here we
right
are.
here.
There we go.
You're still good.
Yeah, let me just start video there. There we go.
So people, there you
Yeah,
have it.
that's it. Okay. So do we have any questions? Yes. Oh, okay. Let's try this. I wear hearing aids, and so I'm a little worried about being able to hear the question, but go ahead and try. Well, no, loud doesn't actually help a lot. It's clarity that helps. But yeah, go ahead.
There at the beginning, you had the idea of like having this connection-based protocol, like something like TCP, or you started with IP first and then added TCP.
No. TCP was the original protocol, and it was all this. Look, just think about it for a minute. In the beginning, I said that we had these multiple networks that already existed. We're not allowed to change anything. And so we had to stick something in between that did something that let a host on one network talk to a host on another net, which is end-to-end. And so we started with one thing, which was to try to make sure that the data got there successfully. And that we had to deal with retransmissions and reordering and packet loss and duplication and all that stuff. So Bob and I started with the TCP stuff. And then around 1977 or so, we're now into like the second or third cycle because we made mistakes in the design and the implementations. And a small group of people, Danny Cohen, John Postel, and a couple of others, pointed out that what we had done was create a reliable transfer. But what we hadn't done is to deal with real-time communication where delivery of everything is not as important as latency. So if you're doing radar tracking, for example, you want to know where the missile is now, not where it was. So retransmitting old tracking data, not of much interest. So we split the IP part off from TCP and then did UDP for the user interface for the real-time communications that didn't care about reliable delivery, but it cared a lot about low latency. So that split happened after the original design of TCP. Yes, sir.
So to your part of the talk about space internet, et cetera, there's been a lot.
Okay, first of all, can you take your hands away from your mouth because I have to see your mouth. Go ahead.
So there's been a lot of commercial hype lately
Yeah.
around space compute, space data centers. Do you have any thoughts there?
I'm sorry, on the commercialization of what?
Space data centers, space compute. Your thoughts?
So I have some relationships with some of the companies that are currently doing space things, Illyria, for example, and Intuitive Machines. It's still pretty speculative about how this will evolve and how quickly it will evolve. But we're in a period of time where space and artificial intelligence are both being heavily capitalized, as you can see. And people who I have great respect for, like Eric Schmidt, former CEO of Google at Relativity Space. So we should be careful to distinguish between heavy investment and outcomes, remembering the dot boom period. But it's pretty clear that there will be a substantial amount of investment and some things will work. The real question in my mind is sustainability of these things. And that's true for both AI and space. In the case of AI, you wonder whether there is a sustainable income that's going to offset the capital expense. And at Google, we think so, because we're making a big investment on the capital side, and we expect to see a comparable revenue increase with applications based on AI. Space is a little bit more speculative, and a couple of reasons for that. One of them is that it's not quite as far as advanced as AI is, but there's another little problem, and that has to do with the fact that we've evolved over a period of, hello? You can call her over there. She's got the other. The problem is we've evolved in a 1G environment for a couple million years or something. And it's not 100% clear at all how well we're going to do as organisms. So people in space is a very big question. Robots in space, on the other hand, we demonstrated can be quite powerful and effective. And of course, right here, I just had a chance to go through the robots lab here. I'm very excited about what you've got going here. This is cool. Now, some of this is going to show up for sure in the space environment. So I am sort of cautiously optimistic about this, but I'm sure there are going to be, just like the dot boom period, a number of dead space companies that didn't have a revenue stream. So that will be the critical question, is how quickly will a revenue stream emerge and what kind of revenue will it be? And I don't have any better intuition than anyone else. Maybe you do. Okay, next question. Yes, sir.
Were you present for the discussions on how large the IP address space should be? And if so,
Absolutely, yes. So here's how this goes. Bob and I are sitting here in 1973. We're just trying to figure out how to do this. And remember, it's an experiment. We don't know if this is going to work, right? But we know that it's intended to become, if it works, it's going to become the backbone of the command and control system for the US. So then we start thinking, well, you know, our allies ought to be part of this because we want the command and control systems to interwork. So we said, so who are our allies in 1973? And there's this list. And then we said, who were our allies 25 years before? And it was a different list. Then we said, who will our allies be 25 years from now? We didn't know. So we thought about it for a while and we said, you know, the only way that we can be assured that all the allies will get access to this is to essentially make it available to everybody, because we didn't know who were going to be our allies. So we didn't patent it. We didn't put any intellectual property protection on it at all. We've released it publicly, and that was deliberate. So then we said, okay, how many networks will there be per country? And we thought, well, maybe there should be at least 2, so there'd be some competition. And we said, how many countries are there? And we didn't know. And there wasn't any Google to ask at the time. So we guessed at 128, and that was wrong, but you know, it was a power of 2, and that's how engineers think. So we said, okay, so 2 networks times 128 is 256, that's 8 bits. And then how many computers per country or per network? And we said, yeah, go for broke. How about 16 million? That's 24 bits. So that's a 32-bit address space. It's essentially 3.4 billion. That's more than there were people in the world at the time. So we thought, well, that ought to be enough for this experiment. And then, you know, if it works, we can have a production version. Well, the experimental version escapes into commercial use in the 1990s. Around 1992, the IETF figures out that we're blasting through Class B 16-bit address space like crazy. And, you know, we've been twiddling bits and trying to make them mean more, support more different networks. So we finally conclude that we should have a different address format. And so we spend 4 years to come up with IP version 6. And in case you're wondering what happened to IP version 5, that was an experiment in broadcasting, which didn't work out. So we, you know, abandoned that. And the next number was IP6. So for IP version 6 is 128. So yes, I was involved in all of those discussions. And we seriously asked ourselves whether the number should be, after we'd done the original design, a few years later, well before 1992, we said, should we adopt a larger address space? And at the time, we couldn't imagine needing, you know, more than several billion addresses. That was before people started putting computers in their pockets and doing all these other things. So I suppose when people say, you know, what would you do differently? You know, I can imagine my 80-year-old self whispering in my 28-year-old self's ear, you need 128 bits of address space. And I'm sure my 28-year-old self would look at my 80-year-old self saying, you idiot, there's no way you could ever need that much address space. And besides, it takes up too much room and so on. I'd never get that. Can you imagine trying to sell the idea in 1973 that you need 4.3 times 10 to the 38th addresses in the internet? Of course, all of you who are paying attention to this know that we've also kind of pissed away a lot of space by splitting it into 264-bit, but 2 to the 64th is still a big number. So the answer is no, we did not realize that we were going to need more then. Yes, sir.
2 questions. One's mine and one's on the chat.
Oh, okay.
Mine first, not the chat. So mine is a little bit in the other direction. Like, you know, the internet has now become the basis of pretty much everything. I don't know if I could even get home today if I could somehow connect the internet. So what are your thoughts these days about, you know, the fact that, you know, part of the internet goes down and what pretty much comes to a stop. If it went down for more than a little while, the world would probably be seriously affected. Like, do you think there should be some structure put around it that tries to ensure that that doesn't happen?
Well, you know, a lot of us have recently asked the question, could you reboot the network from a cold start? And we're not sure. The hard question to answer is what information has to be where to do a cold reboot, and how does it get there? And we don't have a good answer to that. The Marconi Society has a project called Internet Resilience, and it's asking that question and some of the other ones. so the answer is we should be doing something because we're so dependent on this stuff now. I mean, it's deeply penetrated. We had an earlier conversation where I pointed out that we're over dependent on our mobile phones too. I mean, if your mobile phone doesn't work, I guarantee you're going to have a bad day. And that's a signal. That's a really important signal. It says that we're deeply dependent on something that might be fragile. And so efforts should be made to make the system increasingly resilient. Now, there's at Google, for example, we invest very heavily in subsea cable. And I'm part of the global networking team. And of course, we get regular reports about the state of our piece of the internet, which is substantial. And we're getting more cable cuts than pure accident would suggest. And so there's a lot of concern about trying to reinforce the resilience of the system. Another thing, if you've noticed that the subsea cable system is mostly east-west, linking continents together. But if you have a cable cut, there's nowhere to go. If you could put switches at layer 0 on the ocean floor, remember you got to power these things, that's not trivial. But if you did have a north and south capability, you could deal with a cable cut by routing around it. And so there are ideas like that are starting to emerge. But we're deeply conscious at Google, as are others, that this system has become deeply embedded in our economies and our social environment. And we need to care for it even more than we do now.
There's some questions on that.
Okay, he's got a question too, but.
So Ramachwapa asked, how do you help countries with fewer resources get into space? And then there's a related question on what should the research community be doing now to get ahead of the kinds of surprises of AI? So maybe how do we help people get into space? And once we're there, what do we do?
What do we do? So they should read more science fiction, first of all. The whole idea behind science fiction is to speculate about what might happen. So I have made friends with a lot of science fiction authors, David Brin, for example, among others, and Kim Stanley Robinson. Yes, Kim's on. Stan is on the board of one of my nonprofit projects, so we interact a lot together. I'm serious about that, though. The reading science fiction should stimulate your thinking about what's possible. Or what is it? One of the most interesting questions that I would like you to think about is, what is it that you can't do right now, which if you could do, would make a big difference? And that's a wonderful way of formulating a research program. That how do I do X? DARPA does this really well. It's like the self-driving cars. And remember the original DARPA challenge 20 years ago is, what if a car could navigate on its own? What could we do as a result? And what's keeping us from doing that? And so here we are. So that's, yeah, go ahead.
I was going to say one more question.
Okay, well, that's this gentleman here because he had his hand up after you did. Go for it. That's you, yeah.
Yeah, I'll make 2 comments as the guy who actually had his car broken today from Washington today. So one comment is that you were part of designing that protocol. And I think it's the only thing except life that scaled 7 or 8 orders of magnitude from the first network that you showed on the same basic principles. Only life is something that did something like that, except for the internet. So from that perspective, what is the analogy here?
Oh, wow.
And then the second comment, while the internet is so vast and very resilient, in my opinion, it's interesting to note that there is one building in Virginia that 60 to 70% of inter-networking traffic in the world go through that one building. And I'll leave you with that.
Yeah. Well, and actually, I hope you're not right about that anymore. Well, I had hoped that we had more resilience than that. I think the answer, though, to why did this work and how come it scaled is simplicity. Bob and I tried to do the least possible thing we could do to make it possible for end-to-end communication. And everything else was a layer above. And I think that architecture, the layered architecture, which we learned from ARPANET, served us extremely well. And I think that's still the case today. So keep it simple is a really important lesson that you can take away from that. Sir.
Well, we may have, are there any more?
He said that was the last one, so.
Well, I'm the host.
Oh, so there, yeah.
But we may need to be wrapping up.
Go for it.
Not TCP/IP has done so well, but you mentioned two new networking networks, set of networks coming up: space network, and then AI agent network. Yes, do you think TCP/IP will work for both of them?
Oh, well, first of all, the question is, what about TCP/IP, agent networks, and so on? Yeah. Okay. So, well, the architecture, the basic ideas behind the architecture, I think, are still useful, but there may be different protocols, just like the bundle protocol suite is different because of the conditions under which it has to work. So, sorry?
Yeah, okay. Go ahead.
Well, so the point here is that we keep with the simplicity rule, but TCP/IP itself has been augmented, or an alternative called QUIC has been developed that Google is now standardized at IETF, and it does more things than TCP does. And I'm happy about that. So I'm pretty sure that we'll come up with different kinds of protocols. TCP/IP is just a solution to a particular problem. The new problems you've just been describing may require new protocols to solve. Certainly the agent-to-agent stuff.
Yeah, there's another group wanting in.
I'm sorry about that.
Well, my fault for the extra question, but I think we should all give Ben a real
All right, hang on one. Hey, how are you?
So we really do need to
You could just click X.
Yeah.
Thank you so much.